We have the first part of our session today talks about exoplanets, so planets around other stars and how we're beginning to characterize them. The second half of the sessions that we have today talks a little bit about Earth analog environments for the planets in our own system. So I wanted to go through a little bit of an introduction on what we have on the Earth that allows us to learn about other planets and other objects in our solar system. So the first question, this might not work. All right, that's fine. I'll stand over here. Great, okay. All right, so we'll probably always have more data on the Earth than we have on anything else. We're all here on the planet Earth. It's much easier to get to places on the planet Earth than it is to go anywhere else. So as much as we're all super interested in stuff which is not on Earth, if we can find a place on Earth which looks very like the place that we would prefer to be, then that's great. Also, Earth is the only planet with ubiquitous life, right? So we have an example here of an inhabited world. And if we go anywhere on the Earth, right, so far everywhere we've gone, we've been able to find some organism which is living there, thriving there. So if you can go to an environment which is very like the surface of Mars, say, or very like the subsurface ocean on Europa and find life there, well, maybe you found candidate organisms that we might someday find on those other planets. And then the other great thing about Earth is that we've been sort of in this cosmic minefield for 4.5 billion years, scooping up little bits of other planets that happen to be wandering around the solar system. So we've got two talks this afternoon about Martian meteorites, and then additional talks which are about meteorites which aren't from Mars. These are samples of the rest of the universe which have landed on the Earth and then been found by scientists. And these are great laboratories for studying these objects, because so far the only thing we've done to bring back parts of other objects in the solar system is bring back tiny ice grains from a comet. Okay, so a little bit about meteorites. So there's a bunch of different classes of meteorite. Maybe the most important when you talk about the chemicals of life or finding chemicals of life in the universe are these carbonaceous chondrites. So they're called chondrites because they have chondrules. Here's a chondrule, right, this little speck here. And there's lots of these other little circular spherical inclusions in meteorites, which are called chondrules. I don't know why they're called chondrules. It comes from like some Greek root probably that means spherical. So the chondrules are surrounded by this dark matrix. So if people talk about the matrix, they're not talking about that movie. They're talking about this dark, organic, rich material which cements together everything else in the meteorite. So organics are most abundant in the matrix of chondritic meteorites, or carbonaceous chondrites, so-called because they have a lot of carbon. That's what makes them black. So if you actually go and scoop out a little bit of this matrix and look for organic molecules, amino acids, what have you, you'll find them there. So here's just a list of a whole bunch of different compounds which have been found in, I believe, the Murchison Meteorite. And this is a picture of the Murchison Meteorite here. So this is a meteorite which fell in Australia. People saw this streak of a meteor streaking across the sky, landed just outside of town, and like the whole town drove out there in their pickup trucks and found the meteorite. Some people reported that it had a very strong smell, like ammonia. And then they loaded it in the back of a pickup truck, brought it into town, put it in a bank vault, and immediately called the scientists. Like 100% correct. Great job. Because these people preserved the meteorite from alteration. Most meteorites that we find have been sitting there for God knows how long. They've been subject to weathering on the Earth's surface. But these people got there in time to smell the organics coming off of the meteorite. And then they immediately put it in a sterile environment and called the experts. So here's an example of stuff that's been found in these meteorites. If you're sufficiently impressive, you can like write away to NASA and say, please send me part of a meteorite, and they will send you part of a meteorite. You can also go and buy slightly less rare meteorites at your local gem and mineral show. So if you have like an extra $50 and you want a piece of space, you can go there and purchase one. Yeah, so in addition to just finding this stuff in the matrix of these meteorites, You can also do a lot of detailed analysis of the particular kinds of amino acids that you're finding, the particular abundances of the organic molecules that you find. And the abundances that you see might give clues to the formation conditions. So basically, you build a laboratory meteorite under a bunch of different temperature pressure conditions. You run a bunch of syntheses, and you see what you get out in terms of the abundance of the amino acids that you produce. And this might tell you something about what the conditions were like in the meteorite when those amino acids were forming. And in addition, some people think that these organic molecules were the seeds of life. So life and organic molecules didn't begin on the Earth. It began in meteorites and then was brought to the Earth. And then the organic molecules provided the start of life. And I don't know if you've seen recently, it's been going around Facebook and all over the place, like scientists solve 3.5 billion year old mystery of life. And it's basically one particular group has this idea that if only they could get a fancy kind of phosphate, they could make life. And then they said, let's just get it from meteorites. We'll bring it all in from outer space. All these meteorites will land on the Earth and give us the phosphates that we need in order to start life out. So not so much solving a 3.5 billion year old mystery as pushing it back a step to actually being in the meteorites. And now I need to log in again. All right. Okay, so questions worth asking when we talk about amino acids and meteorites. How well known are the formation mechanisms, right? So we talk about maybe characterizing a meteorite on the basis of running a bunch of reactions in the lab, right? You can only run certain reactions. So how well do we know what mechanisms might have been operating in the meteorites when the amino acids actually formed? And if we're looking at meteorites as a source for what happened early on in Earth history, maybe a source for the phosphates or the organic molecules that you need to get life going, it's worthwhile to ask whether the meteorites that fell on Earth when life was beginning are even still around, right? The Earth's surface has been highly processed over the last 4.5 billion years. Maybe we don't even have samples of the stuff that fell on the Earth and might have gotten life started. Questions always worth asking whenever people say, oh, life came from space, is would there have even been a high enough impact flux, right, to matter? Could you ever have put enough stuff on the surface of the Earth that you could get these things started? So even if you have no idea what people say in a talk on meteorites or origin of life beyond Earth, you can ask any of these questions, and they better have a good answer, at least a scientific sounding answer. Okay, so another analog environment that people look at, Brittany this afternoon is going to be talking about ice, and in particular life under ice. So some people think that if you want to get life started, you need oceans worth of water in contact with a silicate exterior of a planet, right? So it's not enough to just have like one pond on the surface of Mars. You need a whole ocean. Not everybody's on board with that, but some people really believe that you need a whole ocean and in contact with a silicate crust. And if you believe that, then one of the best places to look for life in the solar system, maybe in the universe, are the Jovian moons, because they actually have more water in contact with more silicate mantle than the Earth does. So if you believe that life can only begin when you have an ocean in contact with a silicate crust, then you want to go to Europa and look for stuff there. And there's a couple places. So let's go to Europa. So if you're on the surface of Europa, right, there are a couple ideas for where you might have your like cactus, right, living here, getting some sunlight. But you need to always be asking where are the nutrients coming from, where are the oxidants coming from, where are the reductants coming from. Complex life on Earth requires oxygen. We get that oxygen from oxygenic photosynthesis. If you think about these systems where deep under the Earth's oceans, we have superheated water, but then also oxygen in the oceans, which is acting as a battery that life is exploiting, right? So you've got oxidants coming in from outside, you've got reductants coming out from the inside of the Earth, and life can exploit the fact that oxidation wants to happen in order to exist. But you need an oxidant and you need a reductant. On Europa, the idea is that you can take a whole bunch of stuff from the ambient environment around Jupiter, smash it into the surface, and then take that stuff under the shell so that you introduce a lot of oxidants into the Europa environment. And that's the only way that you could get a source of oxidation for the life that may or may not exist inside, like your little cockroaches, that may or may not exist in the near surface of Europa. So I think Brittany's going to talk about finding stuff underneath the ice that has been found in Antarctica. So this is maybe a new environment. Most people, when they think of Europa, they think of this kind of environment, black smoke or deep underneath the ocean. We'd have to send like a submarine all the way down to the bottom of the ocean on Europa. But maybe we could find life really close underneath the ice. So questions worth asking, where is everything coming from? What's the source of nutrients, oxidants, reductants, and energy? And how quickly could any of those be depleted by life, or replenished by life? So you can't just have all four of these things in one place for 30 minutes and then you have life, right? It may have taken a great deal of time for life to get started on the Earth. So even if you have all four of these things, you need to make sure that they're there for long enough and that any life doesn't just get rid of them right away. Okay. Let's go to Mars. So Mars today is very dry. There's lots of evidence for water in the past, but if you put a cup of liquid water out on the surface of Mars today, it would either boil or freeze. So why is that? So here's a plot with temperature on the horizontal axis, pressure on the vertical axis, and this is a phase diagram. So at any particular pressure-temperature pair, water will be in one of three phases, right? Solid, liquid, or vapor. At the Earth, which has an atmospheric pressure of 1 atmosphere, and this temperature range indicated by the yellow line, water can be in all three phases, solid, liquid, or gas. But at Mars, which is at these Arnold's head exploding pressures of, what, 0.006 atmospheres, right? You're down below the triple point of water, so you can never have liquid water on the surface of Mars. You can only have solid or vapor. Now, this is water in its pure form, right? You can like totally throw a whole bunch of chloride salts in there and maybe get water to stay liquid, right? Just like when they put de-icers on the road, the water stays liquid instead of freezing and killing everybody. All right. So there's lots of evidence for past water, even if there can't be liquid water on Mars today. There's shape evidence or morphological evidence in the form of these river deltas. All over Mars, you see shapes which can only be formed by water which was flowing. It's still an open question as to how much water was required to create these features. Some people think that Mars was very cold and dry even when it was warm and wet, right? It was cold and dry in comparison to the Earth. We can also look at mineralogical evidence. So the colors in this image, which is of Jezero crater, I believe it was one of the potential landing sites for the Curiosity rover. Eventually they chose Gale crater over Jezero. But the reason why it was even being considered is because of all this blue and green, which is a mineralogical indication that there are clays there. And these clays, which are called phyllosilicates, because they have silica and because they're layered like phyllo dough, these clays require water in order to form. So if you have water and you have silicates, you can make a clay, make a phyllosilicate clay, and that's what we're seeing from space here via infrared spectroscopy. At least that's what we think we're seeing. You can never really be sure until you go there and pick up a sample and do detailed mineralogy. So we'll have a talk this afternoon about Cerro Negro in Nicaragua, which is one of the youngest volcanoes on the Earth. Emma, when did it first erupt? Do you happen to remember? 1850, right. So there's a historical record of every single eruption that Cerro Negro has experienced, which means if you go there and you're like, look at this interesting rock, you can like look up in the historical almanac exactly when that rock was emplaced, right, exactly when it happened. So we have a historical record of the formation environment for every rock that you might find. Now I have to log in again. For every rock that you might find at Cerro Negro. So you can actually go there, and Emma's going to talk about her work, where she went there with a portable spectrometer, infrared spectrometer, put it right up next to the rock and then brought those rocks back for analysis. So we can actually do a detailed comparison of what you might see on the ground to what you do see from space. And we'll have several other talks about that as well. So here's what you do. Here's what you see from space, right? Here's some more blue stuff, right? That blue stuff here is this iron magnesium smectite clay, right? So whenever you hear the word smectite, you should just think clay. Whenever you hear the word clay, you should think water, right? So the idea here is that this particular band structure, which we think we're observing based on the fit to the spacecraft observed spectra, is characteristic of clay. So you have this lava-rich unit up here, this ultramafic unit, which is basically just lava that came straight out of a volcano. Later on, water can flow through and alter that lava to make these smectite clays. So there are a lot of images like this in the literature on Mars. Bethany Ehlmann is a specialist in this sort of thing. So if you've ever read a paper of hers, she's got lots of these images showing orbital spectra of Mars that say where the water is. But you should always keep in mind that we need to know what it looks like on the ground. One way that we can tell what it looks like on the ground is with these Martian meteorites. So this is ALH 84001. It was found by the Antarctic Search for Meteorites. So they go down to Antarctica and they bring their baseball mitts and they catch meteorites as they come in, right? Because it's very wide and flat. It's very white, so you can see the meteorites coming, and you can actually go and catch them before they ever hit the ground. So this is the story they tell. What they actually do is the meteorites land in Antarctica. There's kilometers of ice above any rocks that came from Earth. And then there's some rocks on top. And so if you see rocks on top of those kilometers of ice, probably they came from space. And in addition, they go to particular regions of Antarctica where the ice has flowed and been brought up to the surface so that you get a collection of a very wide area where the meteorites may have fallen. So they go there, they stay in tents, which are specifically designed to explode if the weather gets bad enough, so that it doesn't collapse on you, right? Because the worst thing would be if the weather gets really bad, then you're like impaled on your tent poles, right? So these are like Scott tents, where if the wind gets fast enough, the top will literally blow off of the tent. And they eat like nothing but frozen steak for months. And every day they get out and they walk like 10 meters away from every other person in the expedition across the ice, and they look for rocks on top of the ice. So this was found in the Allen Hills region of Antarctica in 1984, and it was considered the first most interesting meteorite they found in that year, because inside this meteorite are trapped bubbles of gas which exactly match the composition of the Martian atmosphere. So this is a piece of Mars. Now I have to log in again. This came from Mars. We can tell from multiple lines of evidence, not just the bubbles of gas which are trapped inside it. And so if you're really very, very impressive, you can write to NASA and say, please send me a piece of Mars. I would like to do science on it. And in the 90s, this meteorite was the subject of much public fascination because at least one scientist became convinced that they found fossil life in this meteorite. And there were 3 independent lines of evidence presented in the original paper. Problem is that when you're talking about finding life on another planet, even 3 independent lines of evidence is not enough. And subsequently, I believe all 3 have been separately shown to be capable of being produced by abiotic means. But does anybody remember the name of the guy? Chris McKay. So he was Dave McKay he believed until his death that he had found life on Mars in this meteorite. But you always have to wonder, right? Because, I mean, who knows how long this was sitting there before 1984, right? Maybe it was Antarctic life that like got in there and left those fossils, right, 1 million years ago. So we'll have a talk about differentiating between Antarctic weathering in meteorites and what may have been the original formation environment on Mars. And you can tell a lot from the mineralogy and petrology of these rocks, where they came from on Mars. And I think actually this one turns out to be a little bit weird in comparison to the other Mars meteorites. All right, so questions worth asking, right? What alternate formation mechanisms did you investigate? Emma's going to talk this afternoon about her work in Cerro Negro, where actually they find phyllosilicate clays in this very definitely volcanic environment, right? So there has been aqueous alteration there, but not of the kind that we would expect in like a riverbed, right? So when people see phyllosilicates on Mars, maybe they were formed in a different way than we would expect. Maybe we're fooling ourselves that there's a lot of water there. So you can always ask, what alternate formation mechanisms did you investigate? And then all of these studies of analog environments are always missing something, right? Because they're on Earth, they're not on the other planet. So what is it that's missing? What is it that's wrong about your analog environment? What didn't you consider? Okay. So one particular analog environment that a lot of people study are these Antarctic dry valleys. So they are right here in Antarctica, these dry valleys. That's also so if you zoom in on a map of Antarctica, not all of Antarctica is completely covered in ice. Parts of it are very dry and don't experience any snow over the course of a typical year. So people go to these valleys. They're actually like right here in this background image of the Earth. People go to these valleys and they camp out in, again, these tents which are designed to explode if the weather gets too bad. And these valleys are incredibly well protected in terms of what you are required to do in order to go there. The people who go there have to bottle their urine and take their urine out because it might contaminate the local environment. And in particular, the microbes that live in this lake down here wouldn't necessarily like contaminants getting in there. So these analog environments are really great for a variety of reasons. They're the coldest, driest places on the Earth. They're still a heck of a lot warmer and wetter than a typical place on Mars, but they're the closest that you can get. And occasionally you see things like this, right here, forming in these valleys. And these are formed when water flows in the valley and darkens the soil periodically. We also see these on Mars. We call them slope streaks there. And they're persistent throughout the high latitudes on Mars. I believe they're also seasonal, and they've been observed not only to exist, but also to change over the course of a reasonable time span. So you'll see them like expand and propagate. There are a lot of proposed formation mechanisms for these, some of which do not require water, which gets back to that question, right? What alternate formation mechanisms might there be? Just because this thing we see on the Earth requires water doesn't mean that these things that we see on Mars necessarily require water. So we'll have a talk about slope streaks this afternoon. Another thing that you see in these dry valleys are these really brine-rich ponds. And if water exists on Mars today, it is almost certainly in the form of brines. And one interesting thing that was recently discovered in 2006 by the Phoenix lander are perchlorates, or chlorine salts, that were found on the surface of Mars. They were completely unexpected when they were found. So the Phoenix lander contained a wet chemistry, or a wet soil analyzer, that went to the North Pole of Mars, scooped up a little bit of soil, and looked at what was in that soil, found these perchlorate salts that may explain one of the mysteries of the early Viking landers as to why the life detection experiment had 2 positives and 2 negatives. But these perchlorate salts were found, and these are actually really good at acting as antifreeze for water. So they'll absorb water out of the atmosphere and create a brine, even at the low water concentrations that you see in the atmosphere of Mars. One proposed formation mechanism is that they're produced by UV light interacting with chloride-rich soils. So there's a Death Valley analog, where if you leave a lot of chloride-rich soil out for a very long time under UV light, you can maybe get these perchlorates to form. This is a picture of a trench that was dug by the Phoenix lander. I like to tell my students when I teach an intro class that planetary science is still so new that if you send a shovel to another planet, you're doing literally groundbreaking science. So Phoenix had this little scoop that scooped out a little bit of soil, and then it saw these white spots disappear over the course of several days. And the interpretation was that there's subsurface ice all throughout the northern latitudes of Mars. This is consistent with observations of neutrons, which are made from orbit. There's this subsurface ice mantle tends to absorb neutrons quite well, so there's sort of gaps in what we would expect. in these northerly latitudes. I really got to fix this login problem. I suppose I could plug in. We're really close to the end, so I'm just going to keep going. All right, so questions worth asking, right? Whenever you talk about an analog environment or any of these brines or slope streaks, you could ask, could any known microbe survive in the environment that you're talking about? And there are people working on this. If nothing on Earth could survive in that environment, well, then you have a little bit more of a case to make about why this might be astrobiologically relevant. And then how long, if there was life earlier on when conditions were maybe a little bit better, but things got worse, how long would you preserve any fossil life? Are these slope streaks a good place to look for currently extant microbes, right? Would we be able to find microbe fossils or like little fish fossils in these slope streaks when the water bursts out? It's a worthwhile question to ask, because if you're making a case that this is an astrobiologically interesting phenomenon, we got to talk about whether or not life could exist or whether we could see evidence of fossil life. All right. So that's all that I have. We're going to have, I think that I've covered everybody's talks that I was supposed to cover. If you have questions, you can either ask me, and if I don't know, I will tell you to ask the people who actually know, which are the people who are presenting in the afternoon. Thanks very much. Question?
Yep, so you mentioned that from the last picture you showed was the scoop out from the surface of Mars, and you mentioned that it seems to be that there's some subsurface ice there.
Yeah.
So you made the analogy about anything that falls on Antarctica, the rocks that are above the layer of ice probably came from the sky, came from space. So what do you think that says about Mars if there is a subsurface ice layer, and what that means for the information that we find about Mars, and maybe whether it actually originates from Mars or somewhere else?
Okay, yeah, so I'm going to repeat the question for the benefit of people who may be watching online. So the question is whether, if there is a global subsurface ice layer, or if there is a subsurface ice layer on Mars, what would be the implications for the stuff that's above that ice layer? In particular, when we talk about Antarctica, we have this thick ice layer. The stuff on top is interpreted as having come from space. So one thing is on Mars, the ice layer is not necessarily global. I misspoke when I said global earlier. So it's mostly in the northerly latitudes, so north of about 60 degrees or south of about 60 degrees latitude. And I'm not entirely sure, but I believe that the idea here is that very early on in Mars history, the water sort of settled out in the permafrost layer, very like we have in the northerly latitudes on the Earth. So once Mars gets cold enough, the water ice is stable, not on the surface, but in the subsurface, right? If it's on the surface, it'll vaporize and deposit elsewhere, and maybe later get buried. So you could get layers of soil and ice and soil and ice. And I mean, as far as I know, Phoenix dug like a couple trenches, and then that was it, right? It was buried under the seasonal CO2 frost, which is deposited every winter on Mars. And then, so if you want, you could send a bigger shovel, and that would be like a geologist's dream. Send a bigger shovel to Mars, really scoop out some stuff and see if we can see the strata. You see it a lot in road cuts on the Earth, right? When you cut through a ridge and you can see the layers, right? Geologists would love to do that on Mars, right? And build a highway on Mars and then drive along it. Any other questions? Okay, I think talks will start at